So here let's continue to look into the I would say applications of the deflection of the beam, and in particular here is a special application case that is the beam under distributed loading. And so for this case we are able to rewrite, actually to extend the formulations of the deflection equation here, and let me show you how to do it. So in previous sections we have learned the deflections equations. Deflection equation is d squared y dx squared equal to ei m of x. So why not I put the ei to this the left hand side. Okay, and also from the chapter 5 here we have learned the relations between the shear bending moment diagram to distributed loading. In this case we know the dm dx equal to v and dv dx equal to minus omega, and this is the distributed loading, distributed loading. Okay, and again the there's a sign convention applied. So for example here the distributed loading here positive when is applying downward. This is our sign convention. So basically for this case this is the positive omega x. Okay, so I'm going to try to integrate the both together and see how can we do it. Oh, here typo here, dm dv dx. Okay, so I'm going to integrate the both to see how can we do it. So the integration is this. The first one we observe, if we take the derivative of m equal to v, so from this case I simply take the derivative of the bending moment. Okay, so this one, if this side take a derivative, then the other side also take a derivative, so that is 3 times of the derivations. Okay, so this one from this side we know this one is equal to v. Okay, so furthermore we know the dv dx equal to minus w, so vx. So now here I take the derivative on both sides, so here I take the one more, so that should be the fourth. Okay, so that should be equal to this one, and also this one is equal to minus omega. So from here we come up with this single equations. If you are dealing with a beam is under distributed loading, and you might consider to start with these equations here. Okay, so this is the derived equation, in particular the applicable to a beam is under distributed loading, and compared to our equation, this is the general equation. This is a general equation without any assumption. Basically all kinds of the beams under any kind of the loading, you can start with this one. And for distributed loading case, if you start with this one, that could be easier, but it's didn't say you cannot start with. So let me take say one more time. If you going to use this equation, then this equation can be applied to the solving the deflection of a beam under any kinds of the loading, including distributed loading. Okay, and that will take a little bit more time. However, for the distributed loading case, if you start with this equation, that could save you a little bit time. Oh, okay, a little bit more time. So we see. And on the other side, this equation is the fourth order differential equations. So you have to solve for integrate 4 times. So once you integrate 4 times, you will come up with 4 integrations constant. So that is a 4 integration constants. Then you need to come up with the 4 appropriate boundary conditions. So that is the case we're going to learn in these chapters, and how do we identify the appropriate, the 4 boundary conditions to solve for this one. Okay, if you try to solve for, if you try to start from here. Then the 4 boundary conditions, actually there's a 2, you can in general you can split into 2 categories. And so here we can see for the cantilever beam, and at the site that is the slope, 0 slope, and then 0 displacement. So that is from our the previous one we learned. Okay, on the other side, this is called the free end. At the free end, keep in mind they always have the shearing equal to 0 and moment equal to 0. So the 2 provide you additional 2 needed boundary conditions. So in total you have 1, 2, 3, 4. Okay, and now we'll look at this case, and deflection at the support equal to 0. So that is this case. And again, this is the free end, and this is the free end. So at the free end, no moment, okay, equal to 0. Okay, and so that is this case. And so that is my note for integrating the things. That is the same as the previous page. So we can look at this information here. So from the previous sections, we know we are starting from this equation called the curvature equation. Then we have a slope equation, we have deflection equations. And then here again, this is a summary of what we have done. We take the derivative and of m moment, and we get a v. So we take the one with derivative, get this one. So this equation is called the shear force equation. And again, we take the derivative of the shear force, and we get the distributed loading. So that one we got the distributed equation here. Okay. So from those individual differential equations, we can integrate the individually step by step. So for example, we start from EI d4 dx4 equal to minus omega x. Okay, so if you integrate this one, then you got this equation here. Okay, and that is the integration constant. C1 is the integration constant, that is quantity equivalent to a shear force. And then you integrate this equation one more time, then you got this one. And again, C2 is the additional integration constant, come up with this has the quantity equivalent to bending moment. Okay, so that is the reason why here when we are dealing with this kind of equation, we would come up with 2 additional integration constants, and those 2 additional constants you must looking into the boundary conditions that regarding the shear force or bending moment. Okay, and then the C3 is the constant regard this geometry, which means the slope, and C4 is called the deflection. So basically here we classify into 2 types of the boundary conditions. One is called the force or moment like, and this one is about the geometry, G-O-M-E-T-R-Y, geometry like. So basically there's 2 types of the equations, 2 types, of the boundary conditions. One type is from the force and moment like, and one is the geometry. So from this previous page here, you can see basically this is the moment or for slight boundary conditions like this one, and then this one is a geometry related. Okay, so from here, that is the information, the key information I want to deliver to you. And so here the boundary conditions geometry related, and so here I try to give you more summaries and the two equation the two examples we've seen in the previous slides, and we can try to look at the example here. So this is the case of the constant distributed loading. So we start from here, the omega equal to constant. Okay, so we integrate 1, 2, 3, 4, 4 times. We come up with the 4 integration constant C1, C2, C3, and C4. And here we have 4 boundary conditions, and that is simply copied from the previous example here. So basically this page shows you how to solve for the detail, in detail how to solve for the C1 to C4 here, C1, C2, C3, and C4. So that is the equations. Okay.